Okay, yeah, so just watch for me. If it stops, let me know, okay? Trying this video system out. Okay, very good. So, my practice is that I will go usually for 15 minutes and 1 hour, and then we'll take a break. So let's talk a little about quantum mechanics for about half an hour, and then we'll take a break. So let me start by talking a little bit about history. I have to remember not to write on this thing. It's not in the view of the camera. Let's talk a little bit of history just as a warm-up to the actual formulation of quantum mechanics. Right? And so as you guys may know, quantum mechanics really started in the early 1900s, but the history of it goes back before that. One of the things that got it started was the attempt to explain what the energy distribution of photons were when they were all in the same temperature, when the photon bound. How do we explain what the energy distribution is? So let me begin there. And I won't pretend to be comprehensive at all. Weinberg has a whole chapter on history, so I recommend if you want to read a bit more, just read his whole chapter. But I'm just going to summarize this. Oh, by the way, so I forgot to say, so I'm going to use a mixture of different sources, right? So Weinberg wrote a whole book on quantum mechanics, which you can find online. If you log on to the library's website, and then look for Weinberg's lectures on quantum mechanics. Let me just be more. Then you can actually find a legal copy of the textbook. Right, and so I will follow the flow of the book, although in many situations I'll use my own notes, which is also linked from the syllabus. And then sometimes I would switch over to Sakurai, which is easier to read book. Weinberg writes in a way that I personally find sometimes a bit difficult to understand. I have to make apologies to the second author. I'm using the second edition, but I cannot spell the guy's name. So, but it really started with Sakurai, and because he died halfway through writing the book, so there was a first edition, and then now there's a second edition. Anyway, so those are the sources that I will be using. Okay, so back to history. So the key point, as I was mentioning, is that kind of triggered this was actually the black body radiation of photons. Right, so I won't write down many equations. I just want to briefly mention the history that led up to what we now call quantum mechanics. And here the question is, the key question is, what is the energy spectrum, which means energy is the energy per unit volume per angular frequency. Let me write it in words. You can use frequency or angular frequency, but the point is that this is an observable quantity. Where we can look at the sun, for example, actually these days, the most perfect black body radiation, I don't know if anyone knows here, one of the most perfect black body radiation spectrum that we can measure actually comes from cosmology. So if you have a very sensitive radio telescope, and this is what got these guys, Wilson and Penzias, the Nobel Prize in Physics, many decades ago. They built one of the most sensitive radio telescopes back then. And they were very happy, and they wanted to test it out, and they pointed in the sky. And it turned out that wherever they point in the sky, they got some noise, what they thought was the noise. And they scratched their head and I don't know what's going on. Maybe did a bird poop in the antenna or what? So it turned out that they have accidentally discovered what's now called the cosmic microwave background, which is directly related to black body radiation. So what happened is now, as we understand, was that the early universe was much hotter, had a whole soup of photons lying around, and they were all at the same temperature. And when you have photons are all at the same temperature, they have an energy density that, as a function of frequency, that can be derived purely from statistical mechanical arguments. Okay, so I won't step through the whole thing, but this was a struggle for physicists to understand. So because the measured spectrum at high frequencies which in our modern understanding is high energies, as I will shortly explain, cannot be explained by assuming that light was just waves. Cannot be explained by assuming light is wave, or wave light. In fact, as we now know, light is in both wave and particle, and that's quantum mechanics. But back then, people didn't understand. But if you did, in fact, so what went wrong was that if you tried to explain it using classical waves, then you would find, and there's a short argument in Weinberg, you'll find that the high energy spectrum goes up. It goes to infinity. So it doesn't make sense from that point of view. So it was Planck who first figured out that if you assume that the light coupled to harmonic oscillators, discrete harmonic oscillators. So he did not start off assuming that light itself was particles. That took Einstein. But he did assume that it coupled to discrete harmonic oscillators. Then he was able to derive that rho was in fact, for the time being, I'm going to write that by H bars. So it's H bar over pi squared. And then it is omega q over e to the h bar omega over kt minus 1. Right? So I hope you guys have seen this formula. It's called the Bose distribution. Right? And so if you've gone through an undergraduate curriculum in physics, you should have at least seen and hopefully have derived this Bose-Einstein distribution before. Right? So this is basically now what we call Bose-Einstein. But of course back then that's not what we call it. And in particular what we want to highlight is this is the first time where we have a new fundamental constant in nature. Right? That's why we call it Planck, because Planck was the first one to realize that you can make an argument if you assume photons coupled to discrete oscillators at some temperature T, then you can show that the energy density of the photons themselves will follow this distribution. But at the cost of introducing a new constant, which we now call Planck's constant. So H is Planck's constant. H bar is actually H divided by 2 pi, right? Which is more commonly used for reasons that I'll get to later in the course. So it took Einstein to realize that no, it's not just the photons that couple to discrete oscillators, because what are those things, right? It's actually the photons themselves that actually are discrete. And he postulated this, probably inspired at least partly by that black body, probably but certainly by the photoelectric effect, where he was the first one to realize that the photoelectric effect is what it is, because light comes in discrete packets. So if it comes in discrete packets, and each of them carry H bar omega energy, right, for one photon. And so that means that if your photon does not have enough energy, doesn't matter how many photons you have hitting your metal surface, right? I hope you guys all know photoelectric effect. You have a piece of metal, you shine light on it, and what will happen is that you will kick out electrons from the piece of metal if your photons have high enough energy. But it means that you need every photon that kicks out an electron needs to have enough energy. It doesn't matter how many photons you have. If you have a lot of photons, but all of them do not have high enough frequency, however hard you shine light on your metal, you will never be able to excite any electrons out of it. Right? You just need that minimum energy to kick out the electrons. It's called a work function. You need a minimum amount of energy to do that. And this, in fact, showed that this interpretation is, in fact, consistent with the fact that photons are discrete. And then later on, it was, I can't remember, it was Lorentz who used statistical mechanics ideas that were developed by Gibbs. Right? Gibbs was one of the pioneers of modern day statistical mechanics. But it was Lorentz who applied those ideas to derive this formula for rho. Right. So even though it came from Planck, actually he didn't quite get the right reason for the formula. And this also is a good place to mention, right? So because we're all in graduate school, we're trying to do physics at a research level. You will discover that very often to get to the final answer, to get to a final understanding of the phenomenon, it takes, it's a convoluted route, right? It's not always a straightforward route. And it also tells you that you shouldn't be afraid to guess, right? If you're doing research, you shouldn't be afraid to be wrong. You shouldn't be afraid to make a guess, right? So in some sense, Planck was wrong in the sense that he did not come up with the right reason for his formula. He was right about the formula because we can measure it. So in some sense, it's just a fit to the measured spectrum. But the proper reason behind it took, Einstein and statistical mechanics and Lorentz and so on to get to where we are today, right? Which is why it's now called the Bose-Einstein distribution. There's a reason why the Bose's name is behind it, as we will see later on in the class, right? Because there's also something called the Fermi-Dirac distribution. It turns out that statistical mechanics does not imply this uniquely. There is also another possibility where this is, instead of a minus, you get a plus. You guys probably have seen it if you've gone through statistical mechanics. How many of you have seen this before? Have you guys seen the derivation of this formula in your statistical mechanics course? Yeah. So nobody's raising their hands except you. No? Okay. Okay, don't be shy. Okay, like I said, please be. I know there are quite a few people here, but don't be shy. Especially because I need to know where people are in terms of understanding. Okay, so let me just go on a little bit more, and then we'll take a break and come back. So, this is the beginning of quantum theory. So people were still very skeptical about the existence of photons, right? And so, according to Weinberg, what really solidified people's confidence in the photon hypothesis was the fact that you can, if you imagine photons are particles, then you must be able to scatter photons of other particles, right? So in particular, you should be able to have photons coming in and then scatter off an electron, and then both the electron and the photon will go in their separate directions. Right? So this in fact happens, and this is in fact a proper Feynman diagram, but I won't talk about what that is. So this is actually called quantum scattering, after the guy who in fact measured this effect. Right? So you scatter photons of electrons, and you will in fact see that you would suffer a change in direction based off the assumption that because photons are particles, they carry with them energy and momentum. Right? So in the relativistic notation, I'm going to use non-relative. Energy of h bar omega, and momentum is also h bar k, where k has the same magnitude as the omega. So it's just like colliding billiard balls, basically. If you play pool, right? You knock one ball off the other, you know it obeys basic kinematics, conservation of energy and momentum. And so once people saw that photons obey the same kinematical laws, then they became convinced that photons were behaving like particles. So let me just finish by this part by mentioning that once you accept that photons are particles, it turns out there's a very basic argument that you can make that would then bring you straight to the fact that, the now understood fact that quantum mechanics itself inherently involves probabilities. Okay, so this simple statement has been a YouTube lecture you can find of an MIT professor explaining this. I'm going to link it from my notes, but let me just briefly tell you the gist of the idea, how you can see that. And the basic idea is the existence of polarizers, right? So you know, if you own sunglasses, some of the sunglasses are polarized, made of polarized filters, and you probably have solved these problems before when you were in undergrad, right? So if you have a polarizer, it has a direction of polarization, but so does light. Okay? So light also has a polarization, and you know that the polarization of light basically tells you what's the direction of the E and B fields that are oscillating with time, and this is from the classical point of view. And if you try to pass a polarized light through a polarizer, you will find that this angle here, I'm sorry, the other way around. This angle here, between the electric field and the polarization and direction, determines what is the intensity of light on the other side. So the intensity of light, in fact, will turn out to depend on the angle, and in fact, it will go like cosine squared. Okay, and let me just check that. Right, when theta is 0, that means that this light is lined up with the polarization direction of the polarizer, and then all the light will go through. But if you, and so that's cosine 0, which is 1. And if it's perpendicular, then no light will go through. So cosine of pi over 2 is 0, right? So this is a classical perspective that we can observe. You can just buy yourself a pair of sunglasses, actually 2 pairs of sunglasses, right? The first pair will produce the polarized light that you need, and then the second pair you can rotate it. And you find that when you rotate the second pair of sunglasses in a particular orientation, the image will go completely dark, and this is why. Right? You haven't done it before. It's a very simple thing you can try for yourself. But now, if you believe that photons are also particles, then this is where the probabilistic interpretation of quantum mechanics has to enter. Right? So if you say that you can shoot photons continuously through a polarizer, okay, and you do exactly the same thing. You orient your photon in a particular direction, you keep shooting photons through. So the question is, how can it be that sometimes you get light that goes through, and sometimes you get light that doesn't go through? What do I mean by that? Because how else can you get partial transmission? Right? The fact that you have a cosine theta dependence means how you get partial transmission. Okay, so sometimes you get through, sometimes you don't, because that's what intensity means. If you do exactly the same experiment, orient your photons in exactly the same way, and let's say you shoot 1,000 or maybe 1,000,000 photons through the polarizer, but because there's this cosine squared theta dependence, sometimes the photons won't go through, because otherwise it wouldn't be cosine theta, it will be 1, right? It will be 1. So sometimes it will go through, and sometimes it doesn't. But remember, these are particles. And if you did exactly the same thing over and over again, how else can it be other than the fact that it must be probabilistic, right? Quantum mechanics, if you in fact follows the probabilistic character of quantum mechanics, has to follow if you believe in this polarizer experiment, and this is in fact a nice way to see that it took us a long time to accept this, right? But if you now that in retrospect, you can in fact kind of verify for yourself that quantum mechanics has to be probabilistic. The only caveat is that there are people out there who believe that perhaps there are these hidden variables, meaning there's some other degree of freedom hidden inside the photon that interacts with the polarizer in such a way that it will produce this effect. Sometimes it goes through, sometimes it doesn't, right? And maybe not this semester, but in the next semester, we'll talk about something called the Balanced Inequality. And basically what made John Bell very famous was that he thought very deeply about this quantum mechanics problem of probabilities. And he showed that this cannot be the case as long as certain things are violated, what we call now Bell's inequalities. And these experiments were done. Right? We have now verified that Bell's inequalities are violated, which will not be the case if there were hidden variables. And so many of these hidden variable theories don't hold water. And so the simplest interpretation is that quantum mechanics itself is intrinsically a probabilistic theory. I want to make this side remark because we are talking about photons, but I will return to this at the end of this discussion as well, because this is due to Max Born. Any questions for me at this point? No? Okay, let's take a 10-minute break, and it's 1 right now, right? So let's come back in, I'm sorry, it's 2, right? And so let's come back in 10 minutes. Yeah. No, ask your question. I just want to pause the. Yeah. Oops. Okay, let's start again. So we're talking about photons, and this came out of studying black body radiation. But of course, there's more than that, right? So quantum mechanics came about in large part also due to our attempt to understand atomic physics, right? So this black body energy. So So what happened was that even in the 1800s, we were able to split light coming from hot gases. And we were able to see that the light coming from these gases actually was not a continuous spectrum, but rather it took on discrete lines, either absorption lines or emission lines. Emission lines just means it corresponds to light being emitted by these gases. The absorption lines will be basically light passing through the gas, but being absorbed by these gases, so it became gaps in the appearance of light passing through these gases. So for example, just as a side remark, as an example, you guys might know that helium, right? This helium is actually the second most abundant element in the universe after hydrogen. But the element helium was not discovered on Earth before it was discovered by looking at spectral lines from the sun. So it was first discovered on the sun, so to speak. Not by directly going there, obviously, but we looked at the sun, we found these patterns, and people recognized that this is a new element, right? And only afterwards we found helium on Earth. I heard these days helium is in a short supply, so don't buy too many helium balloons. I heard it's getting rarer and rarer. But this became a problem in itself, this understanding of these discrete lines, because we didn't understand what was going on in these atoms themselves, right? So this poses a problem. So the discrete character of these lines, as well as what's the structure of the atom. Right. How can you understand the light coming from something if you don't understand the underlying structure of that something? Right? And so this is what really gave rise to quantum mechanics proper. Right? It's the dynamics of the photon of the atoms, in particular how electrons orbit around the nucleus, that gave us the Schrodinger Equation and so on. Right? So this is very, very important. So I'm just going to skip over the many details that Weinberg actually talks about in his book. But essentially, it took quite a number of people to discover the neutron, the proton, the electron, and so on. But as we know, and Rutherford actually was one of the big pioneers of this, right? You scatter particles off nuclei or atoms, and you discover that basically there's a nucleus that is composed of protons and neutrons. Obviously, the protons are the ones that are positively charged. How you discovered this was that you can use the electric charge to count how many protons there are. It turns out to always to be an integer multiple of the electron charge. But you can also find out how heavy it is. And that heaviness, it will turn out to be an integer multiple of the heaviness of protons, but it will not be the same Z. It won't be, in other words, the total atomic number. Atomic weight, I think it's supposed to be called atomic weight, is not usually equal to Z. Right? For hydrogen it is, but for many. Okay, so let's see whether this lasts for at least until the end of the class. Okay, so de Broglie had this idea that, remember this was after photons, which used to be waves, are now particles. So what about electrons, which were also just recently discovered at his time, right? So electrons, which were discovered as particles, this is not due to him, but de Broglie decided to think about what happens if electrons themselves are waves. Okay. And this is what started what we call wave mechanics, right? But what he did was really for free particles. As you would learn in a bit, the de Broglie waves are basically of this form, right? The de Broglie waves are basically e to the minus I e t, where e is just k squared over to m. That's the energy, the kinetic energy of the particle. And so what he did was really just for free particles. And so Schrodinger was the guy who came along to realize that you need some way to, for these waves to interact with more non-trivial potentials, where they can't just be waves. But even before that, there was already an experiment by these guys that showed that the Broglie waves the existence of them by scattering electrons of, I think Weinberg was saying, nickel crystals. Okay, so if you have any experience with light scattering, what you find is that people around those times were already able to scatter X-rays of similar crystals. And when you do that, if you've taken a, for example, a solid state physics class, I'm pretty sure you would encounter this problem. You'll find that there will be a diffraction pattern because of the crystal structure, right? Because of the way the atoms are arranged in the crystal, when you shine X-rays off a structure like that, there will be particular angles that are special. It's like taking it's basically taking a Fourier transform of your crystal, roughly speaking. And if electrons themselves are also waves, then the concept should be very similar. If you can take an X-ray or Fourier transform your crystal through scattering of X-rays of the crystal, then you should also be able to do that for electrons as well, if they are waves. And indeed, this was found, right? This was found to be the case, and which then convinced people that yes, electrons are also waves. But like I said earlier, these are free particles essentially, the free particle waves. But what about when the electron resides, that lives inside an atom? How would you explain that part? And so what happened then was Schrodinger came along and he predicted that, or rather he came up with now the well-known Schrodinger equation, right? So Schrodinger there are more details in Weinberg's book, right? So if you're interested in history, just read chapter 1. So I'm skipping over a lot of names and a lot of the intermediate steps. But Schrodinger came along and realized that you need a more sophisticated description. In particular, you need your wave function, this wave function, to in fact interact with potentials. For example, the Coulomb potential produced by the nucleus of an atom. And so this is what eventually led him to realize that the Schrodinger equation, so let me just write it down, is partial T acting on psi, I'm again skipping over many things, and then you have H bar over 2m, Laplacian plus the potential, all acting on psi. So it will turn out, and this is what we're going to explain as the course goes along, this is the kinetic energy, this is the potential energy. So the whole thing is basically the total energy, right? Kinetic plus potential. This is called the Schrodinger equation. And of course, as they like to say, the rest is history. And the reason why we say that is because this is, in fact, our current understanding of how to model atomic phenomena. Right? You need to write down the right potential, and you have to solve this equation, and you'll find that the eigenvalues of these of the energy operator, which I'll talk about a bit more, are in fact superseding whatever Bohr, Sommerfeld, and all the rest of the people have done. Right? It comes out of those energy levels, the discrete energy levels of the atom, comes out of this more fundamental equation, right, the Schrodinger equation. So that's how we got here in terms of quantum mechanics. But it's not all, right? So Heisenberg apparently also has his own, this used to be called wave mechanics. We don't really say it anymore these days, but who is mentioned is called wave mechanics. And Heisenberg had its matrix mechanics. The camera is still running, right? I just want to make sure.
Yeah.
Okay. And then what we're going to do for the rest of this course actually is neither wave nor matrix at a fundamental level. What we're going to adopt as a fundamental perspective is actually due to Paul Dirac. Yeah, so we will see how the formalism of Dirac, in fact, subsumes both what used to be called matrix mechanics and the Schrodinger's wave mechanics. Right? So essentially, roughly speaking, if you already know some quantum mechanics, Heisenberg's formulation was working at the level of the operators. And then these Heisenberg, and then for Schrodinger, he was working in terms of the wave functions. And you can solve for either wave function or for the Heisenberg picture operators. But the underlying structure, which is what we're going to start talking about probably at the beginning of next class, is the notion that at the fundamental level, quantum mechanics is essentially linear algebra. Right? So this is why we're going to spend a good amount of time over the next few weeks, many weeks, going through linear algebra, but phrased in a way that is tailored to understand quantum mechanics. All the notation and so on are all going to be tailored towards understanding quantum mechanics, the language of quantum mechanics, of quantum theory at a fundamental level. And this is due to Paul Dirac. And this is also a good place to mention. So in fact, Dirac was also the man who pushed this even further. And by that I mean there is something called quantum field theory, which is the quantization of fields. Right? And so the reason why this is an issue is because we understood photons, we discovered light as a classical wave first. And then we discovered that it was made of particles. But it turned out that to understand it at a fundamental level, we had to take the field theory of photons and quantize it consistently. And the pioneer in this quantum electrodynamics is, of course, Dirac himself. Right? But of course, this class is not quantum field theory. Some of you might be taking my quantum field theory, but it's not quantum field theory. If you want to hear that, come to my other class. But it is worth mentioning that Dirac is the pioneer who went on to develop the quantum theory of fields. So the last ingredient of the historical development is, of course, the probabilistic character of quantum mechanics itself. Right? So you might be surprised to hear, or maybe you already know, so you're not surprised anymore. But Schrodinger himself, I think, was quoted to have stated he got very uncomfortable with the probabilistic character of quantum mechanics, right? Actually, many people are. Einstein also was very famously uncomfortable with probabilistic character of quantum mechanics. So, my advice is that with the hindsight of history, right, we have gone, more than 100, almost 100 years now. We're now 2020, right? So this thing happened roughly 1925, if I remember the dates correctly, or 1926, 25, I think. So we're nearly 100 years away from the Schrodinger's equation. And so I think we can be more comfortable with this probabilistic character of quantum mechanics. We're not as shocked by it anymore because the many people have came before us, and no one has found some glaring logical inconsistency about having a universe that is inherently probabilistic. Right? Of course, it is completely human to say it is not intuitive. Right? We are at a basic level. We are biological animals, but we're not evolution. In terms of evolution, we did not evolve to feel the probabilistic character of experiments like that, in an intrinsic way. There's nothing in evolution that compels us to be able to understand this at an intuitive level. Same thing for relativity, right? We are not chased around by animals that move at relativistic speeds. So there's no need to understand relativity at a biological level. So there's the same remark for special relativity. It's very unintuitive, and you should not feel guilty that it's very unintuitive. Right? But don't be shocked by it, because we have both relativity and quantum mechanics. We have at least a century of history, and so far has been consistent. All the predictions of these fundamental pillars of modern physics has stood the test of time. Right. So anyway, so let me just mention the very last part about this probabilistic character. I will just mention this in the context of the wave function. Probabilistic. I already mentioned that for the photon case, just by virtue of accepting that photons are particles, so you can do this experiment as many times as you want by sending photon after photon, and then doing exactly the same thing, orienting the spin in a particular way, and then orienting the polarizer in a particular way. You see that it has to be probabilistic. Otherwise, how can this experiment work? Right? How can you do the same thing over and over again, and only cosine squared theta times you get this result of the photon going through, and then 1 minus cosine squared times of doing the same experiment, you get the photon not going through. How else can you explain this than just simply accepting that this is just describing probability, right? But this was not how it began, right? So how it began was that Born, this is called the Born rule, after Max Born, tells us that, in fact, it is quite general. There's a Born rule, but I'm going to state it in terms of the wave function, and then later on, if I have the time, I'll state the more general Born rule. But for the wave function is a function of time and space. So what Born tells us is that this wave function is not some stuff that describes how much of an electron is there, but rather it describes what's the probability that the photon, in this case the electron, can be found at a particular location. and it can be, and it comes about by squaring the wave function in a complex sense, right? So this is a complex wave function because this is a complex equation. But when you square it and then you multiply it by an infinitesimal volume, so this, in fact, is the probability of finding the particle, usually it's an electron, but let's call it a particle, at time t and at location x. The probability, because it's multiplied by this infinitesimal volume. If you just talk about the square of the wave function, then that would be a probability density, or probability per unit volume of finding the particle there. So it was not Schrodinger nor Heisenberg, but it was Max Born, who thought about this thing very hard and came to this conclusion that the consistent way to interpret the wave function is the probabilistic one. And that's why we call it the Born rule. And like I said, because of this uneasiness people have with the probabilistic character of quantum mechanics, even till today, people still ask, is the Born rule fundamental, or can it be derived from something even deeper? But you can still find papers, people still write papers asking this question. And I think it becomes even more interesting to think about when, especially when you're a cosmologist. Right? So I do know a lot of cosmologists like to ask this question, because when we talk about quantum mechanics, usually we're talking about atomic systems, small systems that we can always imagine is embedded in this big macroscopic world that we live in. But what about the universe itself? If quantum mechanics is a fundamental description of nature, then it better also apply to the entire universe, right? And that's when it gets very tricky. Right? What do we mean by the wave function of the universe? What does the Born rule mean in that case? How do you interpret these things? Right? So cosmologists are still very keen on understanding these issues. I don't know if you can test it, but but certainly at a conceptual level, it's something that I think it is very interesting to think about. Okay, any questions for me? No? Okay, don't be shy. Okay? And usually it starts early. Right? If people start asking questions, then the ball starts rolling. But if everybody is shy, then the whole semester you're going to spend staring at me, and I'm going to just stare at you, and then we're not going to talk to each other. Right? That's how you develop a dysfunctional relationship. 不讲话，这样，yeah. Okay. So I only have 10 minutes left, but I will continue with my next topic, which is that I will start talking about quantum mechanics proper by first outlining in the direct sense, in the modern language, what is quantum mechanics, right? And then I'll probably run out of time. But starting next class, which I believe is Thursday, I will begin talking about linear algebra itself. So while I'm erasing the board, you should feel free to think about any questions that you have. Don't be shy. Especially when you get completely lost, and then you tell me you don't know what's going on, then it becomes very, very difficult for me to help you. But anyway, we're just starting, right? But I just want to emphasize this point. All right. Okay. So, what are the basic principles of quantum mechanics? And this is a very, very short summary, right? And it could well be not understandable to some of you. But on this point, don't worry too much because I will spend over the next few weeks going through this linear algebra structure. So the first thing is to recognize that, this is from the modern perspective, that we have a Hilbert space. It's really just a vector space. It's just and this is why linear algebra is so important. Right? To understand what a vector space is, we'll have to define it carefully within linear algebra. But let me just say that quantum mechanical systems are assumed to be essentially vector spaces. Right? If you're talking about the electron going around the nucleus, you talk about some piece of material or some quantum dots, or surface physics or whatever that you care about, that system is assumed, it is governed by quantum mechanics. It has to be a vector space. Right, so there's a direct correspondence between physical systems and their corresponding linear algebraic description. That's the key. And that's all the information there is. Right? There's no additional structure you need to put in and so on. Right? The day you discover that you need additional structure than just linear algebra, that's when you find quantum mechanics is broken down. Right? And then, what about things that we're familiar with that we can observe? Position, momentum, energy, all these things. It turns out that many of these things are permission operators, correspond, I think it's more accurate to say that correspond to permission operators acting on this whatever vector space that corresponds to the physical system, right? So momentum has its operator. We'll see it very soon. Energy has its operator. It's the Hamiltonian that gave us the kinetic plus potential energy in Schrodinger's equation, and so on, right? I do want to say, and here I'm being a little bit of a bit of a rabble here. Many quantum mechanics books will just simply tell you all observables correspond to Hermitian observables, how Hermitian operators. I'm not sure if this is completely true, right? So there are things that you can measure, right? If you want to be very, very strict about it, you need to ask yourself, of all the things that you can measure as an experimentalist, this is why it's good to make friends with experimentalists, right? If you're a theorist, sometimes you can get so caught up with your fantasy world, right, of your pure thought. And you forget to check how are things actually measured in reality. Right? So for example, how do you measure the mass of an elementary particle? Right? Is it an observable in this sense? Right? It turns out that, for example, for mass, you talk to your friends in high energy physics, you count particles coming out of the detector, you make a plot, and you plot it against the outgoing energy or momentum as a function of the particles that you count. And then if you have enough statistics, you find a bump in your distribution, where you try to find where the peak is, and the location is the mass. So tell me how that is related to the eigenvalue of some permission operator. So if you answer this question, I will erase this many. Okay, but I claim many, but not all observables are like. But it is an important concept that many of these observables are permission operations. And then we already talked about the bond rule. So let me just briefly mention what is the more general version of bond rule. So if O is permission, it will turn out that there will be these eigenstates that correspond to O. Again, these symbols right now might be a little foreign, but don't worry, I will explain this in a bit over the course of the next few weeks. And you now ask, what's the probability if your physical system is described by some state psi? What's the probability that I will find the state to be in this eigenstate lambda? And it turns out that the general bond rule that just now you saw as just a square, the wave function telling you the probability density of a particle, finding a particle at x, is now described as psi lambda squared. That's the generalized bond rule. Okay. Again, don't worry too much if this is a little bit abstract for you. And I will come back to this statement when we do. I just want to lay it out first. And then finally, we need to way to describe the dynamics of your physical system. So I told you there's a correspondence between the physical system and a Hilbert space. And so if you take your physical system and this, like I said, lies in this Hilbert space, how does it evolve in time? Okay. That's what dynamics means. Then the answer is the more general form of the Schrodinger equation that you saw earlier. So instead of having a wave function, it's now a vector in the vector space, but I dt acting on it is now the Hamiltonian, which is really just the total energy operator, basically the principles of quantum mechanics. But because it is a little bit abstract, it will take 2 semesters to fully flesh out, actually not even fully, but to have some understanding of what it's talking about. I just want to mention one last side remark before I finish. I know I'm out of time, which is that I was asked this question the last time I taught quantum mechanics, which is why are complex numbers necessary in quantum mechanics? And a straightforward answer is to simply look at the